We are now moving on to Kataoka's criterion. We just completed Roy's criterion. And basically, we're trying to still pick a portfolio based on certain rules. And let's see what Kataoka has to say. What Kataoka says in his rule is that you first pick a probability of lower return that you do not want to cross, and then you pick the maximum lower limit return based on that factor, based on that sort of lower limit of risk that you do not want to cross. Okay, so basically what it's trying to say is if we select alpha to be the probability of a return below some lower level, okay, then we're going to maximize our lower limit return, the return that we picked in Roy's before. We had originally picked the lower bound of return first, but now we're gonna pick the highest lower return that we can get, subject to this sort of inequality. Okay, subject to the fact that the probability that our portfolio return does not fall below that pre-selected alpha that we picked. Okay, the pre-selected risk. So this might sound a little complicated for now, but hopefully when we solve a few of the problems and I kind of explain what's going on through this comparison, it might become a little easier to understand what's going on. Basically, what we're trying to do is find the maximum lower limit return that we can get. Okay. So what did we do in Roy? In Roy, we first picked the lower limit return, right? We said, hey, we do not want to fall below a certain return, say 5%. Okay. Once we said we do not want to fall below this RL, this 5%, then we use that to find how many standard deviations away from the mean that value was. Okay. And then based on that, we found the value that went all the way farthest to the left. Okay. That would give us the lowest probability of obtaining a return below that specific point, right? So basically, we first picked some lower limit. We called that RL. Okay, and then we found what's this area, and then the further left we go, the lower that area is going to be. Okay, the lower the probability is going to be, and we call that alpha. Okay, so we did not go into this much depth when I was going over Roy, because all we're trying to do is to find the RL point that's furthest to the left, right? Basically, that's what we were trying to do. Okay, now in Kataoka, we're doing kind of a reverse Roy. You can think of it that way. Okay, we first pick the probability that we would not like to cross. Okay, we first pick the probability that we do not like to cross. So let me put it in a different color. Okay, we first pick some probability. Let's say this area here is our probability that we do not want to cross. Okay, once we've picked that probability, then you're gonna pick an RL. Okay, you're gonna try to find the reverse of it. Okay, you're gonna try to find what is this value here. Okay, what is this value that we called RL before? What is this value here? Okay, so we'll find out what that value is, and we want to go as far to the right this time as we can. Okay, we want to maximize that lower bound of return that we can. Hopefully that makes sense. If we're trying to lock the probability of a low return, once we've locked it down, we want to try to find as high a return as we can among all those blocked opportunities, basically. Okay, so this we'd first find alpha. Okay, first find alpha, or first select alpha, and then use that to try and find what is the z. Okay, and then use z to find RL. Okay, we want to pick the maximum return. Hopefully this is a little more intuitive. We just want to find the maximum return once we've met all our requirements. Okay, so back to the black. Okay, so for standard normal, when alpha is 0.05, the z value associated with it, the sort of this this point, okay, this point here that we call z, that we use in the Roy's as well to determine how many standard deviations away from the mean we are. That value is minus 1.65. Okay, so this should have been known from the quantitative class, but if you do not know this, most probably whatever alphas I give you, I will also give you the associated z values. Okay, so based on that, you can make some conclusions about the further steps. Okay, I might give you a set of different z values, and you might have to pick one from them. Okay. So anyway, we have this criteria. So if you remember before, right, before we were going about it, we said z is equal to RL minus RP bar over sigma p. Okay, we know this from before. This is how we calculate a z value. Okay, now we're trying to say that, hey, we want to get a z that is not only equal, but it could also be greater. Okay, it could be any value further out from there. So this is just to show you how the textbook arrives at its inequality reference towards the end of this section. Okay, so if we just put a greater than or equal instead of just an equal, now we'll just solve this inequality to just show you how it arrives at what the textbook shows. Okay, now if you bring the sigma p up to the top with the z, we have z times sigma p is greater than or equal RL minus RP bar. Nothing has changed here. We're still in the same equation. Okay. Now we'll bring the RP bar over as well. Okay, so it says RP bar plus Z times sigma P is greater than or equal RL. Okay, what did I do? I just brought this guy over here. Okay, I just brought this over here. It had a negative sign before. Now it becomes a plus. Okay, so now it becomes a positive RP bar. Okay, so now if we're saying RP bar plus Z times sigma P is greater than or equal RL, that's the same thing if you just look at it from the right to left. Okay, if you just look at it from the right to left, if the left side is greater than the right side, that means this is less than this, right? The right side is less than the left side. Okay, that's just what I'm going to write now. So it's RL is less than or equal RP bar plus Z times sigma P. Okay, I didn't change anything. I just rewrote this equation with a less than sign. Okay, and now we've already established what our Z was. Our Z was 1.65. So if you wanted to write that using numbers, we'd have RL is less than or equal RP bar plus. Now it says plus Z, but our Z was a minus 1.65. Okay, our Z value was a minus 1.65, so we convert that to a minus 1.65 times sigma P. Okay, it's just putting it into the textbook format. Okay. Now we also have, if you bring the ZP over, if you bring this Z sigma P over to this side, okay, it's a positive Z sigma P over there. When you bring it to the other side, you'll have RL minus Z times sigma P is less than or equal R bar P. Okay, hopefully that makes sense. I didn't do much. I just brought the ZP over to the RL. Okay, and that's the same thing as doing exactly what we did before. If this side is, if the left side is less than the right side, that means the right side is greater than the left side, right? So I'm going to just rewrite it where the right side is a greater than. RP bar is greater than or equal RL minus Z sigma P. Okay, and now if we put numbers to that, like what we did before, we have RP bar is greater than or equal, okay, RL. Now we have a minus sigma P, minus Z times sigma P here, but Z is minus 1.65, so minus times minus will be a positive, so you're going to get plus, plus 1.65 times sigma P. Okay, so that's basically how the textbook arrived at their equations. Okay, now we rewrite this as an equality so that we're able to plot it. If we just want to see how it looks in a graphical format, this is basically so that we can get to a graphical structure. Okay, we always try to see if we can using graphs. So if we write as an equality, okay, if I'm writing this thing as an equality, you see that this again starts looking like the equation of a line, right? It's where this is the intercept, this is the slope, and then we plot it. Okay, so if we plot it in this form, we see that we wrote it as an equality, right, with RP bar equals RL plus 1.65 sigma p. Okay, we plotted it here, and then we start drawing different RLs, right, because this slope does not change, right? The slope is always 1.65, right? That's why these lines are all parallel. Okay, sigma p does not change. That is just the standard deviation of the system, right? Sigma p, r bar p are axes. Okay, that did not change. Now we're plotting just different starting points, right? Different intercepts. So we start with RL1 and we see that we're kind of cutting that efficient frontier. With RL2, we're kind of going a little higher. At RL3, we hit that point, okay, that point at which we are tangential to the curve. And if you remember, if riskless lending or borrowing is not allowed, this is the only optimal choice that we have, right? So basically, we're going to pick the max RL. And which one is the max RL? The max RL is this one, okay? That's the max RL. So we pick RL3 in this case, okay? So anyway, let's say that we'll do an example now just so you get a better idea of what's going on. So basically, what was our process? We selected an alpha first. Okay, we selected an alpha. That alpha kind of gave us, we selected this alpha that gave us this area. The alpha is the area. Once we had that alpha, we went down to try and find what z was. Once z came up, we used the formula we know from QMB to calculate a z value. Use that to find RL. Okay, this is the formula that we use to find RL. So basically, we're going to do a problem now that examines that, and hopefully you get a better hang of it after that. Okay, so we've set alpha as 0.05. If we say alpha is 0.05, okay, that if we say alpha is 0.05, that gives us a z of minus 1.65. Okay, and we're going to use that here, okay, in this problem. So we have three portfolios. We have portfolio A with a mean average return of 8, standard deviation of 3, B with an average return of 11, standard deviation of 5, C with an average return of 14, standard deviation of 8. Okay, we're still trying to say pick me the best portfolio, okay, the best optimal choice. But who are we restricting ourselves to? We're restricting ourselves to Kataoka, okay? So what does Kataoka say? Pick a probability that you do not want to cross. Once you've picked that area, then find me the return that's the highest based on that, okay? Find me that RL that's the highest out of the three. So we're going to try and fill in these spots, whichever has the highest RL. That's what we pick. Okay, so like I said, when alpha is 0.05, z is minus 1.65, okay? We're going to use that as the lower limit. Once we've assumed equality, we find that RL, and then we know that we can go higher from there, okay? So that's what it means by use this value as the lower limit. Okay, so basically what are we doing? We're going to just solve for this, for the three portfolios, okay? So for any z, the formula is always RL minus RP bar divided by sigma p. Okay, RL, it's always the same formula. Okay, we subtract away a mean divided by the standard deviation every single time. Okay, keep in mind we're dividing the whole thing by the standard deviation and not just one of the terms. Okay, the entire thing is divided by sigma p. Okay, so if we're trying to solve for RL, how would we go about doing that? We take the sigma p over to the z like we've done before, right? We just did it like a minute ago. We take the sigma p up to the top, so it becomes z times sigma p. Then bring this rp bar over to the left side. It becomes a plus, and then we're going to end up with RL equals rp bar plus z times sigma p. Okay, plus Z times sigma P. Okay, so let's do it for the three portfolios. For portfolio A, we have RL for portfolio A is what? What is the expected return for portfolio A? It's 8. Okay, it's 8. Now we have a plus Z, but what's our Z? Our Z is a negative value. So instead of writing plus 1.65, we just write minus 1.65 times the standard deviation of A. Okay, the standard deviation of A is 3. And that gives us a lower bound return of 3.05. Okay, based on our probability, we're saying based on that 5% probability, the lowest return we can get at that probability range is 3.05. Okay, that's the lower bound return. Now, for portfolio B, we do the same thing. We're finding RL for portfolio B. Okay, RL for portfolio B is we still use the same formula, RP bar. What's the expected return for B? It's 11 minus, again, 1.65 times the standard deviation of B. Standard deviation of B is 5. And that turns out to be 11 minus 1.65 times 5 is 2.75%. As you can see, I'm writing on an iPad, so I have a few issues. Things keep disappearing. Things show up the way I do not want them to show up, and so on. So I apologize. Okay, we do the same thing for C. Okay, so for C, we do what's the expected return of C is 14 minus 1.65 times its standard deviation, which is 8. Okay, and once we do that calculation, we get 0.8%. Okay, so let's write them down. We got, let me change the color so you know that I actually calculated that, okay? 3.05%, 2.75%, 0.8%. Okay, and now what was our goal? Our goal was to pick the highest RL that we can find. If we pick the highest, what's the highest number? 3.05%. 3.05% is the best number we can get. So we are going to pick portfolio A. All right. So hopefully this was making sense with Kataoka. So if you want to go over it one more time, basically what did we do in ROI? We picked some lower limit. Okay, we picked some lower RL, and then we tried to find a point that takes us as far to the left as we can. Okay, and that would be the portfolio we choose. How many standard deviations away from the mean can we get? For Kataoka, we first pick an area. Okay, we first pick an area that we do not want to cross. Okay, so we say 5%. I want to limit my risk, my probability of obtaining a certain bad return to 5%. Okay, once we've limited the risk to 5%, we try to find which portfolio gives us the highest return even after limiting ourselves. Okay, so if we've done that, we see that portfolio A gives us the highest return. And once we see that portfolio A gives us the highest return based on our restrictions, we are going to pick portfolio A using Kataoka's rule.